MS Ramaya University of Applied Sciences.
Hi students, let us discuss a case study on controlling temperature on the plant using P, PI and PID controllers. What is a control system? A control system is that means by which any quantity of interest in a machine or mechanism is altered in accordance with a desired manner. Consider, for example, speed control of a fan or motor. The speed of a fan is directly proportional to the applied voltage. By varying the applied voltage using a suitable mechanism such as a speed regulator, the speed of a fan can be controlled. In the above figure, the fan is the mechanism to be controlled. The speed is the quantity of interest. The speed regulator is the control mechanism. All together constitute a control system. What is an open loop control system? Any control system which does not automatically correct for the variations in the output caused due to disturbances is called an open loop system. Examples of open loop control systems: traffic control system, immersible water heater, sprinkler system, timer-based washing machine, and stepper motor. The advantages and disadvantages of open loop control system. Open loop systems are simple in design and construction. These are effective when the output is difficult to measure and are highly stable, but sensitive to disturbances, less accurate and reliable. What is a closed loop control system? A control system which continuously monitors the output and compares it with the desired output to automatically correct the error in the output is called a closed loop control system. Examples of closed loop control systems: automatic water level controller, temperature control mechanisms, servo mechanisms, missile guidance systems, and automatic speed control of systems. Closed loop systems are highly accurate, less sensitive to disturbance, and more reliable, but complex in design and construction and not cost effective. Differences between open loop and closed loop control system is as shown in the table. In many applications, it is not enough to be able to measure a quantity. Often, it is required to control a quantity either to maintain the quantity, for example, temperature, to some fixed value like you expect when you set the wall thermostat, or to make the quantity vary in some predetermined fashion. Consider an example to control temperature, but it could be any physical quantity. First, to control a temperature, it is required to know what the temperature is. Secondly, to compare the measured temperature with the desired temperature, is it too high? Is it too low? How much higher or lower when compared to desired value? Finally, after you have compared where you are at, that is, measured the temperature, and compared it with what you want, that is, the desired temperature, you should take control action. There are numerous ways you can control a variable. Some of the ways to control a variable include the following: to turn a controller on or off. For example, the wall thermostat measures the room temperature and compares it to a set temperature, that is the desired temperature. Then, if the temperature is too high, the thermostat turns the furnace or heater off. If the temperature is too low, the thermostat turns the furnace or heater on. To make the control effort, that is, the amount of fuel fed to the furnace, for example, proportional to the error, that is the difference between where you are and where you want to be. And there are other algorithms that use the error or some function of the error, like the integral of the error, for example, to calculate the control effort. An automatic controller does the same. It compares the actual value of the plant output y of s with a desired value or set value r of s, determines the deviation, also called error e of s, and produces a control signal u of s, which will reduce the deviation to 0 or to a small value. The manner in which the automatic controller produces the control signal is called the control action. The block diagram of a closed loop control system is as shown in the figure, And detailed closed loop control system block diagram for temperature controller has given in the next slide. An automatic controller must detect the actuating error signal, which is usually at a very low power level, and amplify it to a sufficiently high level. Thus, an amplifier is necessary. The output of an automatic controller is fed to a power device such as a pneumatic motor or a valve, a hydraulic motor or an electric motor. Figure shows the block diagram of an industrial automatic controller together with a measuring element. The controller consists of an error detector and an amplifier. The measuring element is a device which converts the output variable into another suitable variable, that is the sensor, which can be used for comparing the output to the reference input signal. This element is in the feedback path of the closed loop system. The set point of the controller must be converted to a reference input of same units as the feedback signal from the measuring element. The amplifier amplifies the power of the actuating error signal, which in turn operates the actuator. The actuator is an element which alters the input to the plant according to the control signal so that the feedback signal may be brought into correspondence with the reference input signal. Proportional control actions. For a controller with proportional control action, the relationship between the output of the controller U of t and the actuating error signal E of t is U of t proportional to E of t. U of t is equal to k suffix b E of t, or in Laplace transform quantities, U of s divided by E of s is equal to k suffix p, where k suffix p is termed as proportional sensitivity or the gain. Integral control actions. In a controller with integral control action, the value of the controller output U of t is changed at a rate proportional to the actuating error signal E of t. That is proportional to the accumulated error tends to slow reaction control mode. In integral control action, U of t is proportional to the integral 0 to t E of t dt. And U of t is equal to k suffix I integral of 0 to t E of t dt. In Laplace transformed quantities, U of s divided by E of s is equal to k suffix I into 1 by s. Derivative control actions. We never use derivative controllers alone. It should be used in combinations with the other modes of the controllers because of its few disadvantages. It never improves the steady state error. It produces saturation effects and also amplifies the noise signals produced in the system. Mathematically, we have U of t proportional to dE of t by dt. That's equal to U of t is equal to k suffix d dE of t divided by dt. In Laplace transformed quantities, U of s divided by E of s is equal to k suffix d into s, where k suffix d is proportional constant, also known as controller gain. Derivative controller is also known as rate controller. PID controller. A PID controller operates on the error in a feedback system and does the following. A PID controller calculates a term proportional to the error, the p term. A PID controller calculates a term proportional to the integral of the error, that is the I term. A PID controller calculates a term proportional to the derivative of the error, that is the d term. The three terms, the p, I and d terms, are added together to produce a control signal that is applied to the system being controlled. Properties of PID. The PID controller can be thought of having a transfer function. The PID controller transfer function can be obtained by adding the three terms. PID of s is equal to k suffix p plus k suffix I by s plus s into k suffix d. The transfer function can be combined into a pole zero form. PID of s is equal to s into k suffix p plus k suffix I plus s into 2 times of k suffix d whole thing divided by s. Since there is a quadratic equation in the numerator. Since there is a quadratic in the numerator, there are two zeros in this transfer function as well as the obvious pole at the origin. S is equal to 0.
Hi students, today we are looking into the characteristic study of an electrical system using different controllers. The controllers used in this experiment are P, PI, PID controller. So the importance of the system is to control the temperature of a plant with respect to the set point that set to the given as an input to the system. The advantage of this particular system is it can control current output temperature as set by the user. If you see the applications of this particular system, it can be used for a temperature controlling circuits in case of a furnace temperature control, whereas manufacturing plants, controlling the temperature of a manufacturing plants, all such applications can be demonstrated by using a simple example. So this system was interfaced with a laptop, whereas the complete controller sitting in a LabVIEW software in a laptop, and the driver circuit as well as the plant will be sitting outside as an hardware. So by using a data acquisition system, we are interfacing the software as well as the hardware which has been developed in-house by using an operational amplifier and transistor. So to demonstrate the importance of a P, PI, PID controller, we have developed a system circuit using operational amplifier interfaced to a plant which is nothing but a transistor, and we are regulating the temperature, or we are maintaining the temperature on top of the transistor as set by the user, which is set in a LabVIEW environment. So for this purpose we are using MyDAC, a data acquisition system which communicates a signal between an hardware and a software. The operators used in this experiment are DC regulated power supply. We look into the DC regulated power supply. This is a single channel variable DC regulated power supply which can vary output voltage from 0 to 30 volts, and the current it can supply up to maximum 10 amps. So this is a switch where if you want to start the supply by using this switch, we can start. These are the different knobs which are available to regulate your current output by using the current set button, and to maintain the output voltage from these two terminals as per required by the user by using these two knob buttons. One is a coarse, other one is a fine. The output voltage produced at this particular terminals can be displayed by using this voltage output, and the current which is drawn by your system can be seen by using this indicator. So these are the different positions of the knob. This is a minimum position and this is a maximum position for the coarse. Similarly, even for the fine, minimum and the maximum, minimum and the maximum. Before turning on this power supply, make sure all the knobs should be in a minimum position so that due to the flickering, it should not affect your circuit. MyDAC. Now we look into the another important hardware which is nothing but data acquisition hardware named as NI MyDAC. This is really important in this experiment because whatever the hardware output that we are getting will be interfaced to a PC using this data acquisition system. The purpose of this data acquisition system is to convert your analog input which is received from your external world to a digital output which can be communicated to your software or which can be communicated to your PC using this particular device. This is a simple handheld device which contains two analog input channels, two analog output channels, as well as one set of digital ports. So if you closely observe here, this is where the terminals we will be interfacing our analog, our sensors as well as the signals which is required to generate to your system or your electrical system from the analog output channels. This also has a provision to give a power supply to your external system like plus or minus 15 volts to operate your op-amp output voltages, as well as 5 volts for the digital output or to power your sensors too. and this is interfaced to your PC by using USB. External power supply may not be required. Whatever the power required to convert from this 5 to 15 volts by using internal buck boost converter is helped. Driver circuit built using op amp. Plant acts as a transistor. This is an hardware circuit developed using operational amplifiers and a transistor to provide current required to generate a temperature on this transistor. Now this is a sensor which is used to measure the temperature on top of this transistor. Since our complete idea was to control the temperature on top of this transistor, it was sensed by using this LM35 temperature sensor. Now if you see, this is an op amp to drive the current required for the op amp from data acquisition device, and these are the resistors which are forcing to provide enough current on the transistor, and a PC installed with a LabVIEW software and few connecting wires. These are the connecting wires to connect your hardware and software based on your circuit diagram. Now let us start the connections of a characteristic study of an electrical system using different controllers based upon the circuit diagram. Now let us start our connections. First we will take MyDAC. So this MyDAC, as I already told you, it contains onboard plus or minus 15 volts, 5 volts power supply to drive the sensor, analog output channel as well as analog input channel, and one set of digital ports. Now the board which has been developed in-house has a 6-pin connector here. The 6-pin the connections has been written over here. Now we will take a 6-pin connector, connecting it here. Now by looking into this color coding, we will interface these wires to NMIDAC. Now if we observe, the first green color wire represents a 5 volts power supply to the sensor. So this green is connecting it to onboard power supply of a MyDAC by using a screw terminal. Yellow is a sensor output. This sensor LM35 is a temperature sensor which gives you the temperature on top of a transistor in terms of an voltage signal. So the sensitivity of this LM35 is 10 millivolt per degree centigrade. So that temperature corresponding voltage is being interfaced to MyDAC. That voltage can be read in a LabVIEW software. And since the analog input channel has two terminals, 0 plus and 0 minus, where whatever the terminals we are interfacing will be interfaced to an instrumentational amplifier, the 0 minus has to be connected to a ground. So we are taking an extra wire and connecting 0 minus to a ground. Now we look into the another wire which is orange. Orange is connected to ground. So any terminal of any ground terminal of NI-MyDAC can be used for this purpose. other terminal is red, which is plus 15 volts. The purpose of this red wire is to power operational amplifier. So since operational amplifier requires two voltage sources, plus 15 plus VCC, minus 15 minus VCC, so this plus 15 and minus 15 is also providing by using onboard plus 15 and minus 15 volts of a MIDAC. So another terminal for minus 15 is a brown wire, so I am taking a brown and connecting it to 15. Minus 15 volts for operational amplifier is given by using a brown wire. Now this brown wire is connecting it to minus 15 volts of onboard voltage source. Then other wire, black wire, which is analog output. Based upon the manipulated output or the controller output, based upon that output, the system will provide a voltage to the plant. So that manipulated variable will be getting out from one of the terminal of NA MIDAC. So now I am using analog output channel to generate an manipulated variable from a system. So this black wire is connecting it to analog output channel. Since MIDAC cannot provide enough current to drive a transistor, we are using another wire to supply power to a transistor by using DC regulator power supply. So the positive terminal of DC regulator power supply is connected to this wire, and here we have a two terminals. The purpose of these two terminals are either by using adapters you can power this board where the 15 volts required to provide a voltage source to the transistors can be by using these two terminals, or by using a DC regulator power supply connecting it to the other terminal at this point can also provide a voltage source to the transistor. And since the ground should be always common, so the ground of a DC regulator power supply is connecting it to any ground terminal of MIDAC. And the sensor, a 3-terminal wire, one is plus VCC. Since this is an active sensor, it requires some voltage. So on the board we have already provided 5 volts from NA MIDAC to this board. So by using these 3 terminal connecting at this particular portion can provide voltage which is required to the sensor, as well as based upon the temperature value, the brown wire, which is the middle pin of LM35, gives you the output voltage based upon the input temperature value. And when I look into the data sheet, it shows us 10 millivolt per degree centigrade. That value is being connected it here. This is being fed to a MIDAC by using analog input channel 0+. And this is the connections for the transistor, the base, collector and emitter terminals, connecting it to another 3-pin connector here. This is an USB cable. This so now we will connect this USB cable to the PC. So whatever the signals whatever the sensor output signals being on top of this transistor will be acquired to a PC by using this USB cable. So the data acquisition device and PC has been interfaced using or being communicated by using this USB cable. This completes our connections. Now we'll start our experiment. So before switching on the DC regulator power supply, make sure all the knobs are in a minimum position. So any fluctuations before switching on may damage your circuit. So in order to not to affect or damage your circuit, make sure all these knobs should be in a minimum position. So once the knobs are in minimum position, just switch on the power supply using this. Now using this coarse and fine, set the voltage required for your experiment by using this coarse and fine. So for this experiment we are using 12 volts output voltage. So now once your voltage, this is a voltage indicator where you can see what is the voltage you are getting out of these two terminals. Once by using a course, once you set your voltage very close to your required voltage, by using the fine knob you can vary the output voltage. Now the current knob a maximum, between the minimum and the maximum. Once we set the connections in power supply, now go to PC side, just open the program used to record and control the data, the temperature on a transistor. So this is the front panel view of an algorithm developed for controlling the temperature on a transistor. So if you observe here, this is the set value where user has to set the required temperature on a transistor, and this is an output which gives you the information of the current temperature on the plant. So in this case our plant is a transistor. So since the plant has a sensor equipped on it, that sensor voltage value converted into the corresponding temperature will be displayed here, and these are the settings which has to be made for tuning the parameters of P, PI, PID. So based upon the settings or based upon the gain factors that we set at this point, the manipulated variable will be dependent on, and this is a screen or a chart which gives you the information about your set point. The white line is your set point and the red line is the corresponding temperature on a transistor or a plant. Now I am setting a temperature to somewhere around 50 degrees centigrade and I am switching on. So the present temperature on a transistor is 44 degrees. Now if you closely observe on the DC regulator power supply, the current drawn by the circuit now is 0.04 amps, and that entirely depends upon the parameters that we set on Kp, Ki and Kd. In this case, this is a PI controller where the Kd value, the gain of a Kd is set to 0. Now once the temperature is very close to the set point, if you closely observe, the current drawn by the system is also decreasing. And if you observe the monitor here, screen here, initially there is a difference between your set point and the output voltage. Now as the time changing, the set point and the output is coming very close to each other. The set value is 49.77 and now the temperature is somewhere around 47.34. Keep on increasing. So based upon this we can understand that there is a error between your set point and your required output. So to decrease that error, which is called an offset error, either we have to increase our integral gain. I'm slightly increasing the integral gain. Now if you observe, because of increase in integral gain as well as a proportional gain, there is a small overshoot, 49.77, 50s. And now, even though if there is an overshoot, because of these parameters, it maintaining the temperature on a transistor to be at the required with plus or minus 2% of an error. If you observe, because of a preset gain parameters of P and I, it is maintaining the temperature, the set value, and the output on a transistor of, it is maintaining of same temperature. Now we will see the effect of a simple P controller on the system. Okay, to understand the effect of a P controller, I am cooling down the temperature on a transistor. So by setting this temperature to 30, and I'll make the integral gain to be 0. Now if you see the system is operating with a simple P controller. Since my I gain is 0, K gain is 0, so even though it has a P and I and D, but since the gains are 0, the controller acting in the system is only P controller. So once the temperature is cooled down, again we will start our experiment with changing the proportional gain, and we will understand the effect of a P controller on a system. Now let us see the effect of a P controller on the system. Now the system has been cooled down to a room temperature. By making the system gains of integral and derivative 0, the controller acting on the system is only P controller. Now we will see the effect on the system with a simple P controller. So now I am increasing the set point to 50 degrees centigrade. If you observe here, depends upon the proportional gain set here, the time taken for the system to reach the required output voltage will always vary. Since the gain value is very small, it takes more time to reach the set point to the required output. Since most of the systems required very fast response, the value that we have set for this particular application may not be enough to make the output with a less time to reach the set point. And even though if you observe, after a particular period of a time, output temperature is within the range of 45 to 46 degrees centigrade. So we can observe that there is small offset available with set point and the output temperature. So by using an integral controller, by increase of integral controller, we can decrease this offset as well as the time taken to reach the system to the set value will be very small. This demonstrates the working of a PI controller on a temperature system. In this system, since this is a heating system, a PID controller is not needed. In case of wherever the PID controller is needed, by simply changing the parameters of D gain, the functionality of a PID controller can be achieved by using the system. This finishes the experiment on study of temperature control on an electrical system by using PI/PID controller.
At MSR UAS, we spark your imagination unlike any other.